for our warm-up today, I asked you to shade the area that's given by these two integrals. And geometrically, when you're looking at an integral from a to b of f of x dx, that's the area under the curve of that function from a to b. And so in this first integral, we have an infinite length of that curve, an infinite domain. And we're going to explore the idea of, can the area under this curve be finite, even though the bounds on our integral are infinite? The integral from 0 to pi over 2 of tan x, that one does not have an upper bound of infinity, but the upper bound, the length of that curve is still infinite because of the vertical asymptote at pi over 2. And so when you're shading that area under the curve between 0 and pi over 2, the question becomes, is that an infinite area as well, or is it possible for it to be finite? There are real world applications, which is why we're exploring this. For example, if you wanted to know the present value of an investment that is going to generate income in perpetuity, then you need to know improper integrals. Half-lives, if you want to do carbon dating, how old is a fossil? With new dating methods, we can now determine something that is as new as a couple hundred years. They can use it to authenticate paintings. The exponential growth and decay with differential equations, which we're going to do in a few weeks. This whole idea of improper integrals comes into play with all of that. All right, but before we jump right into improper integrals, let's talk a little bit about infinity. We mathematicians were a little bit lazy, so we don't want to write grows without bound every single time we're talking about something that is becoming infinitely large. And so instead, we have that infinity symbol. But if you treat infinity like a number, you will lose points. And so just think to yourself, for example, would you say that the limit as x goes to infinity of the square root of x plus 1 is the square root of grows without bound plus 1? No. And since you wouldn't say that, don't write it either. The only time that you would appropriately use infinity, in fact, I'm going to change this to a positive infinity here, is if it's on the other side of an equal sign and all by itself. So a couple of different ways. These examples, they're pretty straightforward, but as we get into more complicated limits, you might like to note to yourself of what's going on inside of there. So let me show you a couple acceptable ways that you can show that something is going to infinity. Okay, so this is proper notation, but if you wanted a little extra to help along the way of what's going on, one thing that you could do is draw an arrow. So this x here is going to infinity. And that works. It's maybe not my favorite method because you're crossing something out. It might make it a little bit harder to see what's going on in the original problem. Another way that you could notate something is that you can kind of use that bad notation without getting into trouble for it are thought bubbles. So we could say something like this is going to, make a big thought bubble here. And you could say that this is e to the negative infinity. And it's in the thought bubble. I won't grade it for better or for worse. That is considered, your own work, your own thought process. Another thing you could do is just label it as scratch work. So you could say something like as the natural log of x goes to infinity. And so maybe 1 over infinity is 0. This is bad notation, but because you labeled it as scratch, I'm going to ignore it. You can do whatever you want there. You won't lose points. But I also won't count it as correct if you have something that you, in hindsight, wanted me to look at. So use it carefully. So we still want to know if this integral from 1 to infinity of 1 over x squared dx is meaningful. And we get into trouble because we don't know how to evaluate an integral when the upper bound is infinity. In order to explore this, we have to fall back on the definition of an integral, which leads us to the fundamental theorem of calculus. I think I put some extra slides in here. There we go. Leads us to the fundamental theorem of calculus, which tells us that if we have a continuous function on a closed interval from a to b, then we can evaluate that integral, and it is equal to f of b minus f of a, where our capital F is any antiderivative of f of x. Now, there's two key words in this definition. First off, f of x has to be a continuous function. And not only does it have to be continuous, it has to be continuous on this closed domain, this closed interval from a to b. So right now, we're running into trouble with both of these integrals because here we have an upper bound of infinity. You might be asked on a written homework, why is it improper? So this would be the wording that you could use as a description. Here, this is, we'll talk about improper in a minute, but here we run into trouble. We cannot use the fundamental theorem of calculus because the width of this interval from 1 to infinity is not finite. And as a side note, this is in your orientation for web work, but anytime you have a bound of infinity, you have the open parentheses because, again, it's not a number. So just notation-wise, be aware of that. Okay, so it's not finite. We cannot use the fundamental theorem of calculus. And while in the integral with the tan x, we don't have an upper bound of infinity, it's still not continuous on that interval. So f of x equal to tan x, not continuous on the closed interval from 0 to pi over 2, since our f of x does not exist at pi over 2. Well, then if we can't use the fundamental theorem of calculus, how can we evaluate these functions? Yes. Okay, so he's saying if we could use some type of limit notation, then we could make this into an integral that was finite. And so we'll work our way up to that. But first, I want to talk about when you need to do that. So let's just identify a few integrals first, whether or not we can use the fundamental theorem of calculus on them. And I said we talk about proper versus improper, and this is a good time to do it. An integral is proper if you can use the fundamental theorem of calculus. Wait, I'm going to rephrase that. No, that's good. We can keep it that way. In other words, we say that an integral is proper if our function f of x is continuous on that closed interval from a to b. And we say it is improper if it's not proper. Easy enough. Sometimes it's going to jump out at you that one of these integrals is improper. For example, if you see a bound of infinity, whether it's an upper bound or a lower bound, these integrals are all improper. So we have another one here. Other times it might not be as obvious. In the top row, middle, we have a discontinuity in that denominator. At x equal to 3, since that would give us a 0 in the denominator. But x equal to -3 is not on our interval. 3 to 5, which means that this integral is proper. In other words, we can use techniques of integration that we already know in order to evaluate this integral. On the bottom left, we have the integral from 0 to 1 of the natural log of x dx. The natural log of 1 is 0. We're okay there, but the natural log of 0 doesn't exist. And so this integral is improper because of that discontinuity at the lower bound. And then for the last one, the integral from -1 to 2 of dx over x, well, we're okay at -1, we're okay at our upper bound of x equal to 2, but there is a discontinuity within that interval at x equal to 0. So the only one that's proper on this page is the top row middle one. The rest of them, we need some other method in order to integrate these. Okay, so let's go back to the fundamental theorem of calculus. If instead of infinity, we had a number as our upper bound, if we wanted to integrate from 1 to 2 or 1 to 5, 1 to any finite number, then it's a proper integral. So in order to use the fundamental theorem of calculus, let's think of this upper bound as, let's call it t. And so now we're looking at the area under the curve from x equal to 1 to some other x equal to t value, which we can evaluate using the fundamental theorem of calculus. So we can say that this integral from 1 to infinity of 1 over x squared dx is equal to, and I'm going to leave a little space here, but for now, we have the integral from 1 to t of 1 over x squared dx. And we can see these are clearly not equal because of the upper bound of infinity there. But what we can do in our math speak is take the limit as t approaches infinity. And the idea here is that first you're evaluating this integral from 1 to t. So you get back a function, you plug in your bounds from 1 to t, and that at that point, then you evaluate the limit. So thinking of it as a two-step process, then we can now apply the fundamental theorem of calculus. Yes?
So it also works if it's like negative infinity, but sort of e there.
Absolutely. So he asked, what if the lower bound is negative infinity? And so we'll explore how to deal with that. But yes, absolutely, we can still evaluate in those cases. So let me give you the technical definition here. If we have an integral from a to t of f of x dx, and it exists for all values of t that are greater than or equal to a, then we can say that the improper integral from a to infinity of f of x dx is equal to the limit as t approaches infinity of f of x dx, provided that that limit exists and that it is a finite number L. In that case, we would say that the integral converges to L. Now we know with limits, you don't actually get to that value, you just get closer and closer to that value. And so here we wouldn't say converges at L. We don't actually get to L, we're converging to L. And if you guys would just take a second and pull your mask up over your nose, I would appreciate it. Thank you all. Alrighty, so it converges to L. That's just your notation there. Otherwise, if it does not converge, then we say that it diverges. Okay, and as you had asked earlier, it also works when we have a lower bound of negative infinity, or when we have a discontinuity on our interval, or any combination of those things. But before we get into those more complicated examples, let's go back to our opening slide and let's finally evaluate this integral. I wrote out the steps for you on the right-hand side. And as you're evaluating improper integrals, you want to just kind of step by step follow along here. So the first thing you have to do, always, 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 is replace the improper bound with t and set up a limit so that you have a proper integral. So we have the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. And just to really emphasize here that this is two separate steps going on here, I'm going to put some brackets to remind us that first we're evaluating this integral. And while we're doing that, we're just going to bring the limit notation down every single step of the way. So we have the limit as t approaches infinity. Inside of our brackets, the integral of 1 over x squared, we can think of that as x to the negative 2. And using our power rule, this becomes negative 1 over x. And we're evaluating that from 1 to t. This is equal to the limit as t approaches infinity. And let's sub in our upper and our lower bound. So at t equal to, or at x equal to t, our upper bound, we have negative 1 over t. And then minus a negative gives us a positive 1 over 1. Now, as t is growing infinitely large, we end up with this sort of, where's my sad thought bubble? We end up with something that is of this form of negative 1 over infinity, and that is getting closer and closer to 0. So that's a very bad notation, but I'm trying to give you an example of how you could sort of think your way through this process. Okay, so the first term, that is going to 0, and because we're no longer having the t as part of our equation, we don't need the limit notation either. So this is equal to 0 plus 1, which is 1. And I actually prefer, if you're trying to show that that first term goes to 0, I think just writing it in as 0 plus 1 does a very nice job of saying that this is where that 0 is coming from. I didn't just forget about that term. But you're not done. This is all of the work, but whenever you're dealing with an improper integral and we're talking about convergence and divergence, your actual answer should be a statement. My earlier lecture pointed out that you don't actually need to write the thus or hence or anything like that. So I'll put it in green. That part's optional. I just like it. The part that you do need, though, is that the integral from 1 to infinity of 1 over x squared dx converges to 1. And that is your final answer. Give me 1 second and then I'll come to you. One thing I do just want to point out is that if you say it converges to 1, don't forget limits converge and diverge too. So if you use the word it, it's going to refer to the closest noun that comes right before it, which means you're talking about the limit and not the integral. So I want you to be very clear that either write down the integral, write down the original integral is how I would like you to put the statement. In the back, you had a question. So asked if we need to state which test we're using. And when we start using tests, absolutely. And by the end of lecture, we'll do that. But for now, it's okay to just say converges to 1. Any other questions on this? Yes. You should always, yes. So if it's a definite integral and has bounds on the integral, then once you integrate, you should always have the bar. Some books, maybe they use instead of a bar, they use kind of more of this kind of thing. If that's what you're used to, that's fine too. You're welcome. Did I see another question out there? Okay. Let's do another one. Here we have the integral from -4 to 0 of dx over x plus 4 quantity squared. We don't have that bound of infinity, but that lower bound of x equal to -4 gives us a 0 in the denominator, or a discontinuity on our interval. And so this is an improper integral. And the first thing we need to do is rewrite it with our limit notation. The limit as t approaches -4 of the integral from t to 0 of dx over x plus 4 quantity squared. Now, if we go back and we look at our interval, we're on this interval from 0 to 4. And if you think of this as the number line, the x-axis, then the left-hand side is where the negative numbers are. The right-hand side is where the positive numbers are. And so really, we're on this interval from 0 to 4. We're not approaching -4 from both sides. Technically, this limit, it's a two-sided limit the way we have it written, which means we would be approaching t equals -4 from both sides, from values greater than, oh, there's a problem. My apologies. This will make more sense. There. So we're approaching -4 only from values between 0 and -4. Overshot a bit. There we go. In other words, we're approaching -4 from the right. And the right, that's where all of the positive values are, the right side of the x-axis. And so the notation we use would be t approaching -4, and then we put a little plus sign to the top right of the -4. You might be able to do this integral in your head, but I wanted a nice straightforward example that we could do a u sub on. So you'd have an example of changing the bounds. So let's let u equal x plus 4. Du is dx. And I always recommend that you start with the upper bound first so that it is in the same order as what we're subbing into the integral. So when x is equal to 0, subbing that in, we have u is equal to 0 plus 4, which is 4 for our upper bound. And for our lower bound, when we have x equal to t, subbing that in place of x, we have our new upper bound of t plus 4. And we're treating this as two separate steps. So all of this u sub, it goes with the integral part. And we don't need to do anything at this point with the limit notation other than just copy it down. We have the limit as t approaches -4 from the right of the integral from t plus 4 to 4 of du over u squared. This is equal to the limit as t approaches -4 from the right. I just keep putting it in red as a reminder to not forget it. And integrating du over u squared, that gives us -1 over u. Switch that to blue. -1 over u from t plus 4 to 4. This is equal to the limit as t approaches -4 from the right, and subbing in our bounds, we have -1 over 4, and then minus a negative becomes a positive 1 over t plus 4. Now, going back to our number line, we're approaching -4 with values that are bigger than -4. So think -3, -3.5, -3.99. And as we're getting closer and closer to -4, in this denominator, we're always going to have a positive number, which is important because it affects whether this limit is going to positive infinity or negative infinity. And so if you wanted to use your thought bubble, you could think of this as going to 1 over a positive 0. So a very, very small number, but positive small number, which will give you positive infinity. Fit it. Something that is growing infinitely large, -1/4, is still growing infinitely large. So we say that this limit goes to positive infinity. Therefore, the integral from -4 to 0 of dx over x plus 4 quantity squared diverges to positive infinity. Now, this is one case where we differ from the book. The book would just say that this integral does not exist. But if you can specify that it's going to positive infinity or negative infinity, you should specify. So I'll move that. You can't see it because of the Y. Okay. So use one-sided limits when you need to, and be careful with u subs that you do change your bounds. Questions on this one? Yes.
Can I get a reiteration
Sure. So asked why this 1 over here, you were asking, yes? Oh, this one. Going to positive infinity. Okay, so we're looking specifically at this first term there. And so as t is going to negative infinity, as t is going to -4 from the right, in the denominator, we're getting something very, very close to 0. Are you okay with that part? Okay, so then think of something really, really close to 0, like maybe 1 over 100, 100. So 1 over 100 is 100. And then as you get even closer and closer to 0, so say in the denominator, we had maybe just 1 over a million. So 1 over 1 over a million is a million. And so as the denominator is getting smaller and smaller, closer to 0, that makes the entire term go to infinity. Yes.
So then if you were approaching -4 from the left, would we say 1 over -1 over -0 is equal to -infinity?
Okay, excellent question. So he had asked if we, instead of approaching -4 from the right, if we'd been approaching -4 from the left, then in the denominator, this value would be negative, very, very close to 0, but a negative number. And that would make this whole 1 over the t plus 4 go to negative infinity. Yes. Yep. Which is why it's important to use the one-sided limits and then look at whether you're subbing in values slightly larger or slightly smaller. Yes.
So how do you know to use approach from the right or approach from the left?
How do you know whether to use the approaching from the right or from the left? So look at your interval on the original integral. And you can even put a little number line down like I did. So from -4 to 0. And we're looking at values of x that are in between -4 and 0. And so as we're getting closer and closer to -4, but we have to stay on this interval, then we have to be approaching it from values that are bigger than -4. And then I just keep straight the plus and the minus part by thinking of a number line. So if we think of this as our x-axis and the negative numbers are on the left and the positive numbers are on the right, then I think it's a little bit easier to keep up with the notation that this positive means values that are greater than -4 or from the right. Yes. I'm sorry, I'm having trouble hearing your question. Where I'm pointing, or okay, so they asked if we're allowed to put infinity here on this side of the equal sign, and yes, because it's all by itself. It doesn't. We're not saying -1/4 plus infinity or infinity, squared, or we're not treating it as a number. Here we're treating it as this limit is growing without bound. So great question. Yes. So how do we know if the integral is converging or diverging? What word do we use? And since we were able to, in this example, it did not go to a number. So if the limit goes to some finite number, like in the previous example, this limit went to 1, we say it converges. If it does not converge, then it diverges. Any other questions on this one? Okay. Did I lose a page? Okay. In example 2, we had an upper bound of infinity. Nope, that would have been example 1. We had an upper bound of infinity. In example 2, the one we just did, we had a discontinuity on one of our bounds. But I wanted to go over some more complicated examples where maybe the integral is improper because of both bounds or has a discontinuity or multiple discontinuities on that interval. And so example 3, really, we're just focusing on the bounds. In part A, this integral is improper because of both the lower bound, giving us a 0 in the denominator, and the upper bound being infinite. And we can only evaluate an improper integral if one of the bounds is improper. So we need to split this up into 2 separate integrals. So we can say that this is equal to the integral from 3 to some number plus the integral from whatever that number is to infinity. And you can really pick where you split this. You could split this at 4, you could split this at 3.0001, you could split this at 1,000,000, as long as it lies on that interval from 3 to infinity. But seeing that x minus 3 in the denominator and knowing that we are going to have to evaluate these bounds, splitting it at 4 makes sense because that'll make it an easy bound for us to evaluate the integrand in, or the antiderivative in. So once you have it split, then we can deal with each of the improper bounds individually. For the first integral, we would say that this is equal to the limit as a approaches 3 from the right, because we're on the interval from 3 to 4, of the integral from a to 4, plus the limit as b approaches infinity of the integral from 4 to b. Now, just a side note here, I was using t for my limits before, but when we start dealing with 2, I don't like to use t because then the next thing you think of is s, and s's look like 5s. So I try to never put an s in my notation as a variable, just because it's so easy to make a really common, silly, mistake of counting it as a 5. So I switch to a and b anytime we're needing more than one limit. Okay, in part B, this is improper because of a discontinuity at 2, at x equal to 2. And so now it does matter where you split the integral. You have to split it at that discontinuity. So we'll have the integral from 1 to 2 plus the integral from 2 to 3. And introducing our limit notation then, this would be the limit as a approaches 2, and when we're on the interval from 1 to 2, we'll be approaching it from the left. Integral from 1 to a, plus the limit as b approaches 2 from the right of b, the integral from b to 3. Now, in both of these cases, part A and in part B, you want to evaluate each integral separately. And we'll talk about that in the next example. But it will make your life a lot easier if you just evaluate them separately and then take a step back and look at the conclusion based on that. Yes?
If you're evaluating things separately, one of them x's and one of them has like a's or u's or variables, they both still live on the same level.
So even if you're evaluating them separately, you would still want to keep the integrands in terms of x's. But the limits, you would still want to keep them as you'd want to use a and b for the limits, something different on each one, just because it makes it less likely that you would make a copy mistake somewhere along the way. Yes? I missed part of the question, but I know the gist of what you were saying is if one of them goes to a finite number and the other part goes to positive infinity, how do we evaluate that overall? Excellent question, and that's my next example. But if one piece goes to positive infinity or negative infinity, you're done, the whole thing diverges. Okay. And then I just threw in C for fun, so you can see, I'm not gonna ask you to do one like that, but that is a very complicated one where you're having a discontinuity at +1, -1, and both bounds. Are these clarification questions, or did I just want to, I might need to see, can you see me after class for any additional questions? I just want to try to get a little bit through to the next example for you guys. Okay. So this is, okay, so we have the integral from 1 to infinity of 1/x dx. And we will start this the exact same way as the previous examples. This is improper because of that upper bound of infinity. So we'll rewrite it as the limit as t approaches infinity of the integral from 1 to t of 1/x dx. This is equal to the limit as t approaches infinity, integrating 1/x, we get the natural log of x. Now, you can put the absolute value signs in because it's not wrong, but also noting that because we are on the interval from 1 to t, and those are all positive values, the absolute value of something that's already positive is just that thing itself. So in this case, it would be okay to drop them, but if you're in doubt, then there's no reason to just leave them in there. All right, so let's evaluate this. Limit as t approaches infinity of the natural log of t minus the natural log of 1. Natural log and y equal to e to the x, you should have a visual of what those look like because it'll make it much easier and quicker for you to evaluate these limits. The natural log of t as t goes to infinity, that is grows without bound, it goes to positive infinity, and natural log of 1, that is 0. And so this limit is equal to positive infinity. And so the improper integral from 1 to infinity of 1/x dx diverges to positive infinity. Now, this was very similar to our first example from the opening slide when we integrated from 1 to infinity of 1/x squared. And in that case, we said that it converged. So just comparing the two, so far from these two examples, we know that if we have the integral from 1 to infinity of dx over x raised to some number, we have p for power, that will converge from example 1 when p is equal to 2. And we found that it diverges when p is equal to 1. That's from this current example, example 4. And we could generalize, we could actually integrate this and we would find, I will spare you the proof, but we'll find that we can generalize this to say that this integral from 1 to infinity of 1/x to the p will converge for all values of p when it's greater than 1. So when p is greater than 1, and diverges when p is less than or equal to 1. And this is the definition that your book gives, but I'm okay. This lower bound doesn't have to be 1. It can be any value, we'll call it a. So So the lower bound can be any number as long as that number is greater than 0. Because at 0, then we have a discontinuity at that lower bound because 1 over 0 is undefined. So that lower bound can be a 2 or a 5, and you'll still be able to use the p-integral test. So now in this example, we want to determine whether the improper integral from 1 to infinity of 1 over x to the 1/3 dx converges or diverges. Previously, we would have had to integrate this, but now that we have the p-integral test, we can simply state there's 3 parts to it. So first, identify it as a p-integral. Second, state the p-value, whatever power x is raised to. In this case, we have p is equal to 1/3. And the third part of your proof is its relationship with 1. So 1/3 is less than or equal to 1. Therefore, the integral from 1 to infinity of 1 over x to the 1/3 dx diverges. And this goes back to an earlier question in lecture. Do we need to name our test? Now that we have a test, absolutely, you need to name your test. So by the p-integral test. So a full credit solution has those 3 pieces. Identify it as a p-integral, state the p-value, and then either less than or equal to 1 or greater than 1. One thing that I want to make sure I point out, this is not a p-integral. It looks a lot like example 5, but now in the denominator, we don't have x raised to some power p. We have x minus 1 raised to some power. And so you cannot use the p-integral test. This example I will post. It gets back to the earlier question of when you break it up into 2 separate pieces, if one piece diverges, then what do we say about the whole thing? The following examples after that, I will talk about on Wednesday. So it's the comparison test, and we'll follow up with another example. So just bring your lecture notes back with you on Wednesday, and we'll do 1 or 2 more of these examples before we jump into Wednesday's lecture. Alrighty, guys, have a wonderful day, and I will see you guys back here on Wednesday.